Welcome everybody to today's class where we are talking about buffer solutions. Today we will look at the following learning outcomes where we are going to define buffer solutions. We'll be able to differentiate between acidic and alkaline buffer solutions. We should be able to describe how buffer solution works and perform calculations related to buffer solutions. I am excited to start the class with you, and I believe you're also excited to enjoy the class. Let's go ahead. Let's start by defining what a buffer solution is. As you can see, the definition says a buffer solution is the one which resists changes in pH when small quantity of an acid or an alkaline are added to it. If you think about it very well, they say it is a solution that resists changes in pH. So a solution that has to resist changes in pH should be an acidic solution or an alkaline solution. Because whenever we talk about pH, we are talking about an acid or an alkaline. So this is what will take us to two types or two examples of buffer solution, because we've established that it should be an acidic solution or an alkaline solution because we are talking about changing in the pH. So let's focus our attention on acidic buffer solutions. So an acidic buffer solution is the one which has a pH less than 7. Of course, we know that pH of an acid is always lesser than 7. So if a buffer solution has a pH less than 7, it means that buffer solution is an acidic buffer solution. They are commonly made from a weak acid and one of its salts. So most of the time we use sodium salt as the salt of that weak acid. And a very good example of an acidic buffer solution is a mixture of ethanoic acid. Of course, we know that ethanoic acid is a weak acid. So this is the choosing weak acid at this point. And one of the salts we are choosing is sodium ethanoate. Remember we said a mixture of a weak acid and one of the salt, and that salt is often sodium salt. So that is why we are choosing sodium ethanoate here as the salt of the weak acid, which is ethanoic acid. So if the mixture of that weak acid, that is the mixture of ethanoic acid and sodium ethanoate, contained an equimolar concentration of both acid and the salt, that is, if you have an equimolar of ethanoic acid and sodium ethanoate mixed together, or for example, if you have like 2 mole per dm cube of ethanoic acid and 2 mole per dm cube of sodium ethanoate, and we mix them together, we are going to have a pH of 4.76, which is going to be the pH of our buffer solution. So it doesn't matter whether you use high concentration of both of them or you use low concentration of both of them, you're still going to have a pH of 4.76. For alkaline buffer solutions, their pH has to be greater than 7. Remember, pH of alkaline solution is greater than 7. Alkaline buffer solutions are commonly made from a weak base and one of the salts. And a very good example is a mixture of ammonia solution and ammonium chloride solution. Just like in the case of acidic buffer solution. So if you mix an equimolar proportion, for example, if you mix like 3 mole per dm cube of alkaline solution to 3 mole per dm cube of ammonium chloride solution, you're going to get a pH which is equal to 9.25. It doesn't matter whether the concentration you choose is high or the concentration you use is low. So far, the conc of both weak, that is the conc of ammonium chloride solution and the concentration of ammonia solution is the same, you're going to have a pH of 9.25. So let's answer the question, how do buffer solutions work? So we'll start by looking at the definition of buffer solution. Remember, a buffer solution is a solution that resists changes in pH whenever a small amount of acid or an alkaline are added to it. So a buffer solution should contain something that will remove any hydrogen ions that is added to it in order to resist change in the pH, or it must contain something that will remove any extra hydroxide ion that is added to it in order to resist any change in the pH. So if it cannot do that, it means the pH of the solution will change. And when the pH of the solution changes, it means that solution is no longer a buffer solution. So we are going to explain this concept by looking at acidic buffer solutions. And the example we are going to use is a buffer solution that contains ethanoic acid and sodium ethanoate. The formula of ethanoic acid is CH3COOH, and sodium ethanoate is CH3COONA. So first, let's write an equation representing the dissociation of ethanoic acid in an aqueous solution. So that equation is going to be CH3COOH. So remember, ethanoic acid is a weak acid, so it means the reaction will be a reversible reaction because there will be an equilibrium establishment between ethanoic acid and the salts and the ions that are formed, which are CH3COO minus and hydrogen ion. So what this equilibrium establishment means is that we have high amount, that is high concentration of undissolved ethanoic acid, and then we have less concentration or low concentration of ethanoate ions in the solution. So the reason why we have high amount of ethanoic acid, remember, because most of this ethanoic acid are not dissolved in the solution. Now we are going to add sodium ethanoate into this solution. So let's look at the equation for the dissociation of sodium ethanoate first. Sodium ethanoate is CH3COONA. Sodium ethanoate will dissociate completely, so it will give us ethanoate ions, CH3COO minus, just like ethanoic acid, and then it will give us sodium ion instead of a hydrogen ion. If sodium ethanoate dissociates completely, we will not have any sodium ethanoate left in the solution when it dissociates because it dissociates completely. So all of this will dissociate and we are going to have high amount of ethanoate ion, that is high concentration of these ions, and then of course high concentration of sodium ion, but we are not using sodium ions for this explanation. Now, if you have a mixture of ethanoic acid and sodium ethanoate, so you should be convinced that we are going to have high concentration of ethanoic acid and high concentration of ethanoate ion in the solution. So we have high amount of ethanoic acid and high amount of ethanoate ion in the solution. So what will this one do to us, and how will this one help to resist the pH of any additional hydrogen ion or hydroxide ion in the solution? So let's rewrite this equation as a single equation, C3COOH, which is high concentration this time around, and then with ethanoate ion, which is CH3COO minus, which is also high concentration because we get that from sodium ethanoate, which is an aqueous solution, plus hydrogen ion. So we need only the hydrogen. Now, what will happen when we add an acid to this buffer solution? So remember, an acid will introduce hydrogen ion. For example, let me write the equation, dissociation equation for hydrochloric acid. So hydrochloric acid, when it dissociates, it will give us hydrogen ion and a chloride ion. So by adding hydrochloric acid solution into this buffer solution above here, we are introducing an extra hydrogen ion into this solution. And remember, we said a buffer solution is a solution that will resist any change in pH whenever a small amount of an acid is added to it or a small amount of an alkaline is added to it. Some of this ethanoate ion that we have in the solution will react with the extra hydrogen ion that we add to the solution. So something like this will happen. CH3, COO minus plus H plus. This reaction will happen. So this CH3COO minus from the high amount of this that we have, and then this H plus is the new H plus that we are introducing from hydrochloric acid. So when the ethanoate ion react with the hydrogen ion concentration, so it means the pH of that solution will not reduce and will no longer reduce, because what will reduce the pH is this extra hydrogen ion that we're adding to it. But when it gets to this solution, it will be taken care of by the ethanoate ion that we have in the solution. So it means that buffer solution will prevent the reduction or would resist the reduction in the pH. So that is how the buffer solution will resist any change in the pH when we add an acid to it. Although the pH will reduce, but it will reduce just a little bit. Now let's add an alkaline solution to this buffer solution. So I will write the equation again just for us to have it in our mind. So the equation is CH3 COOH, COOH, which is our ethanoic acid. So having an equilibrium establishment with CH3COO minus, which is our ethanoate ion, aqueous, and the hydrogen ion, which is also aqueous. Remember, we have high concentration of this. High concentration because most of it are not dissolved. And then we also have high concentration of our ethanoate ion. This one we get it from the sodium ethanoate, the salt of ethanoic acid that we add. Now, if we add an alkaline solution to this buffer solution, remember, an alkaline solution will introduce OH minus. For example, when we add sodium hydroxide solution, sodium hydroxide solution will dissociate into sodium ion and hydroxide ion. So it means when we add sodium hydroxide, we are introducing an alkaline solution into this buffer solution. So how will this buffer solution prevent or resist change in the pH when we add sodium hydroxide solution into it? When we add hydroxide ion, that is an alkali, into the solution, this will be taken care of by the high concentration of ethanoic acid that we have in the solution. So in that case, this solution has acted as a buffer solution. It resists significant difference, that is significant increase in the pH when you add an alkaline solution to it, and also resist significant decrease in the pH when we add an acidic solution into it. So let's look at how to calculate the pH of a buffer solution. So if you want to calculate the pH of a buffer solution, you need the following. So you need the following variables. Number one, you need to know the Ka of the weak acid. So the Ka of the weak acid is very important for you to calculate the pH of a buffer solution. And you need the equilibrium concentration of the weak acid and its conjugate base, that is an salt. So let me write it: equilibrium concentrations of the weak acid, the weak acid, and its salt. So you need this. So based on this, let's look at this example. In this example, we are asked to calculate the pH of a buffer solution that contains 0.00 mole per dm cube propanoic acid and 0.8 mole per dm cube sodium propanoate, and the Ka of the propanoic acid is given as 1.35 times 10 to the power of minus 5 mole per dm cube. So let's look at how we are going to do the calculation. So the first thing we are going to do is to write the equilibrium expression for this solution. So remember, we have propanoic acid, which is C2H5COOH at equilibrium with the salt, which is C2H5COO minus, and the hydrogen ion. So remember, aqueous. Don't forget, if they ask you to write the equation, you need to put the state of the species in the equation. Now we have the equation, so we will derive the equilibrium establishment for this equation. So let me move up a little bit. So the Ka for this is going to be the concentration of the reactant, which is, the concentration of the product, which is hydrogen ion, and the ethanoate ion, propanoate ion, C2H5COO minus, divided by the concentration of the propanoic acid, which is C2H5COOH. Now, so we need to make remember, we are calculating the pH. So it is something, the pH has to do with the concentration of hydrogen ion. So we need to make the conc of the hydrogen ion as the subject of the formula. So let's do that. So hydrogen ion concentration, H plus. So this one will give us the Ka times the concentration of our propanoic acid, C2H5COOH, divided by the concentration of the ethanoate propanoate ion, C2H5COO minus. So the Ka is given already, which is I think it's 1.35, right? Yes, it is 1.35. 1.35 times 10 to the power of minus 5 multiplied by the concentration of the propanoic acid, which is 0.6, divided by the concentration of propanoate ion, which is 0.800. So if you do the calculation, you're going to get 1.01 times 10 to the power of minus 5 mole per dm cube. So that is the conc of the hydrogen ion. But we are asked to calculate the pH, not the conc of the hydrogen ion. So how do we calculate the pH? We calculate the pH from the conc of hydrogen ion. Remember, pH of a solution equals minus log of the concentration of hydrogen ion of that solution. So, and then we know that the conc of hydrogen ion is 1.05, 1.01 times 10 to the power of minus 5. So if you press your calculator, you're going to get minus 4.99, which is 4.99. So this is the pH of this buffer solution. And this is how to calculate the pH of a buffer solution. Any buffer solution given, just look at the conc of the acid. and conc of the salt, or if it is a base, look at the conc of the base and that of the salt, and then they will give you the Ka of the acid or Ka of the base. So with this, we come to the end of this class, and I believe you've learned a lot from the class. Thank you so much. See you next time.